We're happy to have Geoffrey Compere tell us about angular momentum in GR, the role of generalized BMS symmetry. So go for it.
Thank you. So I'm sorry I was not here last week. I was a late participant. So I was asked to present a review on angular momentum in general relativity, and I will try to be as general as possible and to talk to the audience. And I will mostly base the discussion on these three papers and try to expand it a bit. So it's with my collaborators David Nichols, Roberto Oliveri and Ali Seraj, and Adrien Ferrucci and Romain Rosiconi. So there were some questions last week, and so please ask your questions now. And please, this is an informal talk, so you should interrupt me at any time. Angular momentum in general relativity. So the aim is to isolate first SO3 subgroup of the diffeomorphism group in a suitable sense, close to non-infinity, and then associate to it a Hamiltonian generator or some charge with suitable properties. And of course, angular momentum doesn't come alone. There's also the center of mass. And as you know, well, there are two definitions of center of mass really, even in Newtonian gravity. I mean, if you have any word line and then with some momentum p, either you can talk about the center of mass at initial time, I would call it ki, it would be the conserved center of mass, or you can talk about the co-moving center of mass, the center of mass moving along the impulsion of the body, and I would call it J, GI, sorry. And then, so there will be, so there will be SO3,1 subgroup of the diffeomorphism group to be identified, and then a further step is to isolate SO3 subgroup out of it. So I will separate my talk into three parts to specify the angular momentum. One part is to specify the supertranslation frame. So as you know, there is a BMS ambiguity, a supertranslation ambiguity, what in the frames of non-infinity, and so we have to specify that. Alternatively, we have to give a formulation which is supertranslation independent, and that will give you a non-local type definition. I can talk about it a bit as well. Then the second step is to really talk about the representation by charges, and there I will emphasize the one parameter ambiguity that naturally occurs. I will call it the alpha ambiguity. And this is where the generalized BMS symmetry is relevant to discuss it. And then the third step is to isolate the SO3 subgroup of the Lorentz group. So to go in the center of mass frame, and it's not totally obvious because the momentum is changing with time because it's not conserved. It evolves, there is a loss, Bondi loss. So that requires some thoughts as well. Okay. So for the supertranslations, so the symptotic symmetry group at non-infinity, well, it's not, maybe I should say it's not known because it's not clear yet how big it can be, but it contains BMS, the one found by Bondi, Misner, Sachs, and Metzner, Vandenberg, yeah, I was liking one. And it is the group, so it contains the Lorentz subgroup, and contains the supertranslations, so which are well labeled by a function over the sphere, and they all commute. This is why I call it a vect. It's just a bunch of commuting vectors, infinitesimal vectors, depending on an arbitrary function on the sphere. There's an extension of it called generalized BMS, where the Lorentz subgroup is extended to the full diffeomorphism on the sphere. And it's very natural because you have charges associated to them that are non-trivial, especially for scattering.
We don't know, do we, that all those charges are non-trivial? Couldn't it be that the quotient of diff S by conformal symmetries is trivial?
Well, the natural ones, I would say, just classically would be diff S2 because all the functions are regular. One just naturally introduces spherical harmonics and a basis of regular functions.
But that's not the argument you were making. That you were saying they were all non-trivial. I haven't seen any. I haven't seen any demonstration that there's anything non-trivial in the quotient of diff S with the conformal group.
With you mean the global conformal group or the
infinite dimensional one?
Infinite dimensional one.
Yeah.
Yeah. I mean,
it's my suspicion that that's what it is, though I wouldn't claim to have shown it.
Yeah, so that I will not address here. So because I will just take regular functions. I will assume all the functions are regular.
But you did assert that it was non-trivial.
I can show you why it's non-trivial. Yeah, so I will show you an argument why diff S2 is non-trivial.
But the quotient. There are no elements that the quotient could be trivial.
Well, yeah, with the two Virasorows.
It's important for holography because if it's diff S2, the holographic dual has to be a topological field theory, which are really hard to find. And if it's it just seems impossible. And if it's the conformal group, the holographic dual could be a conformal field theory.
Yeah, I see. So, but that differs.
I think the quotient is trivial.
Okay, well, that I don't know for sure.
I'm not claiming I've shown it. That's my suspicion, because I certainly haven't seen a demonstration that diff S2. I certainly haven't seen a demonstration that the quotient is non-trivial.
Yeah, I see what you mean. So I will not give you an answer here. I will just take this diff S2 simply because the functions are all regular. So I prefer that one here for this discussion than the conformal group, because simply by regularity.
Well, certainly people have been discussing the singular action of the conformal group on the sphere and for 40 years, and it's not mathematically, it's mathematically very well defined how you handle it. Anyway, go on. This is
I mean,
this gets said a lot, so I thought I would speak up.
So yeah, because but let's go back to that one. Once I present the charges associated to diff S2 for scattering, because all these charges are just regular. And
but that doesn't mean that the quotient is non-trivial.
No, indeed, I'm not saying that. So all right, so so this is the symmetry group that we know. So now at all these functions are functions. So the symmetry group is determined by functions over the sphere, and the dependence in the retarded coordinate in U is fixed by the choice of gauge, therefore one can specify this group as special infinity, and it will just, if one fixes a frame as special infinity, which one can do classically. For quantum mechanically is different because there might be non-trivial states, etc. But for classical purposes, it's possible to fix it at special infinity to obtain diffeomorphism invariant notions, at least under this under those diffeomorphisms. So if one fixes, so one looks at it's not this one. one fixes, so scribe plus minus, which is the u going to minus infinity at large radius. So one takes first the r going to infinity, and then u going to minus infinity. Then one can impose boundary conditions there, and in particular fix a frame. So the specification of the frame there would fix it for the entire scribe plus. So that's a way to deal with supertranslations, to fix the frame at special infinity. And then one can know in which frame one is describing all the quantities at null infinity. So one can make that more precise in boundary gauge. So this is boundary gauge. One chooses UR and XA. And then imposes the gauge fixing conditions, and then the condition of the determinant. So there probably, yeah, there were already many talks about BMS, so I'm not going to explain that much more. We just have to use the angular part to define the shear and the body mass aspect, and then the angular momentum aspect is defined here. So I don't know if I should explain any of this. So if you can tell me what what I should explain, what you don't know already. So if I take as boundary condition when u goes to plus minus infinity, so these conditions, so those are the ones that are now everybody is using. So if we take fixed metric on the sphere, and then CB, which is given by these asymptotic values. So only an electric type component, and the value of the C will differ between the past of null infinity and the future null infinity, which is the displacement memory effect, related to displacement memory effect. But
what
now
is sorry, what is the denominator of C plus and minus? What is this thing?
This is just the velocity of light here.
Okay.
The velocity. Yeah, we'll keep the velocity of light everywhere. But since I have two C's, I have C, which is so the capital C would be the defined by this boundary condition here. That's the capital C, and the small c will be the velocity of light. And I have also C indices, I'm sorry. So sometimes the indices will be, but if you see a C in the index, it's just a repeated index over the sphere. So there are three C's, but they all can be distinguished. So here,
and there is the term linear in U at U going to plus or minus infinity.
Yes. So now, right. So what is that term? So usually one fixes, so in boundary gauge, one fixes the metric, which is the metric on the sphere, unit metric on the sphere. But actually, you are not forced to do that. You can have any metric. So any metric that depends on your angular type coordinates. And then you have an extra term in the behavior of CAB. So I call it NAB vac, but actually was found already by Gerock. It's called rho AB up to a trace in Gerock. In asymptotic analysis of spacetimes. And indeed, you have a linear U divergence there of CAB then, if you allow an arbitrary metric on the sphere. That's the way CAB behaves. And so actually, if you look at the news, so the news NAB, which it would be actually the U derivative of CAB minus NAB vac. So that's the physical news.
That's the Weil tensor.
That's the Weil tensor. That's right. That's the Weil tensor. So NAB vac does not, you can turn it on without having the Weil tensor turned on. So note something also. Once you have defined you have an arbitrary boundary metric. The lowest harmonic of C also fixed by the boundary condition, because here you see that from this term, it doesn't fix the L equals 0 and 1 harmonics of C. So they're not fixed simply because they are killed by the differential operator. And that represents the position, like a center of mass. But they are fixed from this term. So if you are in a frame now, which is not a boundary frame with unit geometric, these lowest harmonics are also fixed. Well, just a remark. Yeah. Okay.
But by the way, NAB VAC satisfies something. It's a function of what here?
So NAB VAC, yeah.
The
So
constant tensor, symmetric trace-free tensor on the two sphere.
Yeah, so its divergence is given. It depends on the Ricci of the boundary metric. So in fact, you can write it as a Liouville stress energy tensor so it depends only on gamma AB, and you can write it up to a trace as a Liouville stress energy tensor, where the Liouville field is it can be extracted from the metric gamma AB. So if you do more precisely, if you do a super boost. So okay, what is a super boost? If you decompose the DFS2 into two parts, you can decompose it into super rotation and a super boost, depending on the sign of the on the polarization of on the parity property. So let me try to explain that. It's a bit too much to explain in one shot. So if you have a vector on the two sphere, you can always decompose it into two parts. You can write it. You can write the first part like this one, and you have another part. This one. Okay, so any vector can be decomposed like this. So Helmholtz decomposition. Those ones generalize the rotations. So we call them super rotations, because the rotations are the L=1 harmonics of, if you put L=1 harmonic here, you get the rotations. And these ones generalize the boosts. So we call them super boosts. So they are arbitrary harmonics here. And so they generate the entire DFS2. So if you if you act with a finite super boost on a metric which is the unit metric over the sphere, you will find a new metric which depends on the super boost if generator, and then that's what I call the Liouville field. Then you can build a stress sensor for this field, and that will give you the NAB VAC. So if you want the details of this, you can check. We have a construction with Adrien and Romain in a paper that was actually before that one. I forgot the name, but yeah, the paper just before that one, if you want the explicit construction. Probably all of this is already written in a Gerock in 1970, but it's written in a very different language using a geometric formalism. So here we just work in boundary gauge and write all this explicitly. Okay.
And can one not say I can fix gamma bar AB to be the round sphere, and then NAB is what? What is this?
Then it's 0.
So all this is gauge? Yes.
So it appears only when you look at representation of the DFS2 symmetry. So if you go into the BMS group and you want to fix this DFS2, you reduce it to the Lorentz here. You make that reduction, and you want to keep the metric to be the unit metric, and then this NAB VAC disappears.
Okay. We want, by the way, I'm a bit lost. We want to fix angular momentum. So if you introduce a big baggage of extra gauge freedom, does it help?
Yeah, I understand the question. So at this point, it doesn't seem that it helps, right? So you want to remove this, but I discussed it because you will see later on why. Because the charge, there is really a nice property of the representation of this DFS2. But let me just introduce it for the moment, and then you can gauge fix it you can gauge fix it if you want to SO331. I just wanted to define everything.
But
yes.
But could you say, isn't it true that there are, is it true? I think it's true that there are conserved charges in gravitational scattering that you miss?
Yeah, you miss, if you
And
want to use the DFS2, you miss a lot of charges.
Right. If you just go to regular,
Okay, you know what? Let me just directly go into
right,
that, because
there are conservation laws and that you miss regular.
That's right.
It's mostly about the boundary conditions at the boundaries of Scry, right?
Let me just go to that directly. So let me just give you the explicit, if I can find my slide. Well, you can see all the talk already, but doesn't matter. So here are the charges. So let me just take the example of scattering, because anyway, that's the topic of the workshop. So now let's take endpoint classical scattering in the limit where the length between the objects go to infinity. So you look at early times. So you want that the distance between all the objects goes to infinity. Then the mass, the Bondi mass, and the angular momentum aspect take these forms. So then this is in terms of the individual masses and factors, boost factors and velocities of the individual bodies. And then for the NA, it takes these nonlinear terms are here, depending on the Bondi mass and then the value of C at minus infinity. And then you have the angular momenta of the individual bodies with some direction dependent, depending on all of them have a specific direction. So then the DFS2 charges is, we will see that, but it's basically the integral over the sphere of NA RA, where RA is an arbitrary DFS2. So since the harmonic, if you decompose this in spherical harmonics RA, and then you all these charges, and you take n sufficiently large, you can have all the charges that are independent from each other, because they will depend on the directions of the angular momentum and on the individual masses and so on. So if you just look at 3 charges, it's not enough to describe your system. You want to describe all the charges, and then you can reconstruct. You could do the inverse transform. You can try from all these charges. You can reconstruct what is J and the directions for each individual mass.
But the only source of infinite information here is C minus, an infinite number of multiples, no? All the rest are finite number of data.
Yeah. I'm just taking n. I can take n to infinity. So for given an n, you want to have enough charges to describe your system. I can take an arbitrary number, so you need all of them. So this is why the DFS2 charges are fundamental, because you need all of them to be able to describe what is the individual angular momenta of each of your particles. So as diffeomorphisms, they're not really interesting, but as charges, they're very interesting. And this is also why I use DFS2 and not Virasolo's, because here everything is regular. So I want to think about decomposing in spherical harmonics. So this is why I made the choice here. Okay, so now let's go back. So that clarifies. So now, since the charges are interesting, I also want to look at the action of the symmetries, how they act on the phase space, because now I want to do representation theory. And so to have a phase space, you need both. You need the charges and the action on the phase space. So this is why I need to consider this. Okay, so so once we fix the boundary condition at Scry plus minus, we can fix all the defects to there and all the super translations. So to find back to find back a Lorentz. So by imposing the boundary condition that NAB vac is 0, it fixes, all defects to accept the Lorentz group. And by fixing the unit sphere metric, by the two conditions. So it's a choice of boundary condition that can be enforced. Okay, so now what about the second step? So finding the Lorentz group is not enough, and even dealing with supertranslation is not enough because there's the alpha ambiguity. So what is the alpha ambiguity? So here is the charge written in Bondi gauge, which is the charge depending on alpha. So here is an arbitrary defect 2, but if we restrict to Lorentz, it would just be Lorentz. Na is the Bondi mass aspect that was defined from the metric component. All these are quadratic in the shear, and alpha is this arbitrary parameter here. And I use the measure on the sphere.
Na is the angular momentum aspect, right?
It's the angular momentum aspect defined using your conventions.
Right.
And
Okay.
the one of Flanagan and Nichols as well. So it's not the Barnish-Brown convention. Is
and right now these things are conserved for any alpha, right?
Yeah, so they're evolved flux balance equations for any alpha, and at special infinity, they give all of them the angular momentum of Kerr. I will explain all the properties of this for any alpha. I will explain what they obey. I have a long list here.
Okay.
Of properties they obey. So for the angular momentum, you want to choose RA to be given by this. So all of you are probably familiar with a different definition of angular momentum. I will try to make contact as much as I can with the literature, with standard formulae and so on. So, but this is the formula written in Bondi gauge. So for angular momentum, you want to define the vector, which is the L=1 harmonic here, just the unit vector Ni. There is a minus sign, it's just a convention, standard world convention. And that's it, that's defined. So now you have these two terms here. One depends on, there is a total divergence here. You can integrate by parts, because if you have integral of dA of something, it would be 0. dA of R of some vector, so of anything, it would be 0. So you can integrate by parts, and since this vector is divergence free, this ambiguity, the ambiguity here, this part does not matter for angular momentum. So I can just drop it to write here this way. For the center of mass, the Coulombic center of mass, this is this vector, which is curl free, but its divergence is non-zero. So the two terms matter. So they both appear. So that's the co-moving center of mass, which depends on the value of alpha. Okay, so all these charges obey nice properties. So the first property is that they are 0 for Minkowski in the standard coordinate system. The second property is that they reduce to Kerr in the center of mass frame to the Kerr expressions. So center of mass 0 and angular momentum J. They are all locally constructed from tensors at scribe plus, right, from CAB, NA, etc. And then they obey the BMS algebra at scribe plus minus, so at the past of future infinity. So here is the BMS algebra. So they have this relationship. So it skips it. Yeah, they have this one. So D is just defined here. So it's an operation that generates a function starting from T, which is a super translation, depending arbitrarily on the sphere, and R, a vector on the sphere. You generate a new function on the sphere. And so when you act with a Lorentz generator on the super translation supermomentum on the charges of this super translation, you generate a supermomentum with a specific super translation given by dr of t. So that's the standard BMS algebra. And then the other part is this part where you generate a bracket, standard bracket in a two-dimensional sense. So on the sphere of these two generators of the super rotations or simply rotations.
Sorry, can I ask a question?
Yes.
So if you have an axisymmetric space-time, so like a head-on black hole merger, then we would expect there not to be any angular momentum flux and just obey, the usual Compere formula. But whenever you have alpha not 1, then you have a non-zero momentum flux. Do you have any way to resolve that?
Yes, that's right. So so indeed, so the alpha equals 1 reproduces the Wald-Zupas formula, which reduces to the Compere integral. And so it's and you say that for head-on collision, the Compere formula is 0. I don't see why, but
well, it's just shown that that formula produces no flux of angular momentum, which we would expect due to the symmetry.
Okay, so this okay, I didn't study that case. So you say that for the axisymmetric case, the Compere formula gives you a 0 answer.
Right, but everything else will give you a non-zero answer.
Yes.
So I don't know. When I saw this so-called ambiguity, I just don't see how that is resolved for these axisymmetric cases, unless there's something strange with frame dragging going on. But that doesn't seem very sensible to me either.
Okay, so I didn't look at that requirement. So I have a list of requirements here.
Okay.
What you proposed to me that you write an additional requirement, which is to look at axisymmetric case that you don't expect any angular momentum in this axisymmetric radiation case. I didn't look at that, so I will have to look at that.
Okay, yeah, I've been talking with Nicholas about this, and it was brought up by Kartik Prabhu, but yeah, it would be interesting to discuss this more.
Yeah, because here, so these terms, they add a different way to deal with the. Right. Well, okay, I will have to look at that, but they add a piece depending on the radiation, which is 0 for axisymmetric spacetimes, for stationary spacetime. Sorry. Now you look at axisymmetric non-stationary. Also here, if there is no magnetic part of the magnetic part of the radiation of CAB, that term also will vanish. So I don't know if you in the axisymmetric case. Are you sure that the magnetic part of the shear will be turned on? So is it the claim? Because if in the axisymmetric case, the magnetic part of the shear is not turned on because of the symmetry, then that term will vanish. The alpha term will also not contribute. But that I'm not sure. So
I would have to double check as well.
That might be a way out, but I'm not sure. I didn't look at that, but. I think that's the question. If in axisymmetric case, the magnetic part of the shear for some reason vanishes or not, and then that term will not contribute as well.
Okay, thank you.
This is the thing I didn't. Yeah, I will have to check then.
Geoffrey?
Yes.
If I understand what you're writing here, it looks to me like the Lorentz charges. One would want something you call the Lorentz charges to obey the Lorentz algebra. We lost the important equation.
Oh.
The Lorentz charges you would want to obey the Lorentz algebra, and the Poincare charge, something you call Poincare charges, you'd want it to obey the Poincare algebra. But here it seems like the Lorentz charges indeed obey what you're calling Lorentz charges obey the Lorentz algebra, but when you append translations, you're not getting the or are you? Is that
no,
the
is that the
Poincare algebra? What's this?
Yeah, that's the Poincare algebra. Yeah, it's not.
Oh, that is the Poincare algebra.
Yeah. So for the lowest harmonics, it reduces to Poincare algebra.
Okay. So
The way to
you
generalize
might
it
have said that they should obey the Poincare algebra, not the BMS algebra, right? It's a closed algebra.
Yeah. So
It's a much stronger requirement. You want your charges to obey the Poincare algebra, not the BMS algebra. Well, it's a subgroup.
Wait. I have to be careful here. So there is a Poincare algebra in there, but if you act with a super translation, which is yes, yeah, indeed, there is a. I think that's a statement. There is a Poincare subalgebra of this with all the lowest harmonics, and now the commutator of a super translation PT with P, where T is a higher harmonic on the J, will reduce this to harmonics here that also contain the translations. So the translation will also, the usual momenta will also appear on the right hand side here of when you act with like higher harmonics of P. So in that sense, there's no unique way to define what something like proper super translation, that would be pure super translation, not containing translations, because the translation always show up on the right hand side of this algebra. So there's no proper super translation, but there is there are translations, and there are Lorentz. So there is sub Poincare algebra. Yes, I think that's correct. So okay, so we have that. So they all obey. So the point is that for any alpha, they obey this, because alpha equals 1 is the standard case that everybody uses, and alpha equals 0 is the one that well, Andy used and we used as well, and we check that algebra, special infinity for alpha equals 0. So it's so it should be true for any value of alpha by linearity. So here is the definition of P, just the momentum, the standard definition. Once we generalize with this NAB vac. So that appeared in many places if you check HTCAR, for example. Okay, so for all these definitions, they obey flux balance laws. And then all these flux balance laws are consistent with the leading and subleading self-gravity theorems, simply because boundary terms that we add to the charges do not matter. Only the total fluxes integrated over stripe plus matter. And actually, these ambiguity does not change the total fluxes, because this ambiguity will vanish for stationary spacetimes. And so it does not change the overall value of the fluxes. So for any value of alpha, one can recover the subleading self-gravity theorems. So here is the match with the literature. So alpha equals 1 is, maybe the first one was Landau-Lifshitz. So if we take the pseudo tensor of Landau-Lifshitz and use it to build, like use the Noether theorem and in a post-Minkowskian framework, and one extends quadratic order and then computes the charge associated to rotations of Minkowski for that action, and then writes down the Noether current. So we using the Landau-Lifshitz pseudo tensor. Once find that definition alpha equals 1, and so definition is also the one of Thorne of multiple symmetries, and then it was also found by Strobel using all these formalism reproduces the flux by HTK Strobel. While Zupas have this way to prescribe exactly the fluxes, and it's the same definition. Okay, so this is what we checked a bit that this definition agree. And alpha equals 0, well, it seems that it was introduced here. I don't see an earlier place and then used in these papers. And then another paper, Bonga-Poisson, used actually alpha equals 3, which is different prescription. So now the point is that different values of alpha lead to an effect. It's not zero, so it's important to see how we represent these charges. So it was computed by David Nichols. Here, there's a 0.1% they obtain approximately effect if we compute this change for alpha order 1 for binary black hole mergers. Okay, so it's important.
Is it important here to say that in the out states there is only like one stationary body? Are you saying that in a scattering situation, all values of alpha after integration gives the same angular momentum loss between -infinity and +infinity for the matter part? What is the statement here? You did not write the fluxes.
No. I should. Yeah. Let me give the statement. So in non-radiative regions, so not stationary but non-radiative, so it can be scattering. It can be the end state of scattering. So in non-radiative regions, the boundary condition here is written above. This one, this boundary condition will hold. And therefore, there will be only an electric part for CAB, for the shear. And this part actually, if we make some integration by parts, using the property that R is, R is given by this, is a curl. And using the fact that C is only electric, all these terms will cancel. So this does not lead to any change for non-radiative regions. The only change is during the non-radiative part of
radiative part.
The radiative part of at intermediate places. So it is due to the fact that we need the magnetic part of the shear to have that quantity non-zero. So the magnetic part of the shear will from in u going to -infinity to +infinity, will start at 0 and then be non-zero and then go back to 0. So that term will be maximal at the place, where you have the magnetic part of the shear in the intermediate times, which is maximum.
Mm-hmm.
So this is where it was computed. The approximate numbers is at intermediate times where the magnetic part of the shear is the strongest.
But let's see. You're not saying, are you, that there's, I mean, the difference between the charges for different alpha is also conserved, and we could set up experiments to measure any of these. So there's no ambiguity in the outcome of an experiment.
No, indeed.
It's just a question of
what we mean by the angular momentum. Yeah. Right.
What exactly our experiment measures. It might, if we might have an experiment which measures the angular momentum loss, and then we might have another one that measures the angular momentum plus one of these other conserved charges.
That's right. It's not all experiment. I mean, it's
no puzzle here.
It's not a change of observables. It's a change of what we mean by angular momentum. If we want to, angular momentum is well-defined quantity. We want it to be unique up to this, super translation ambiguity, center of mass frame ambiguity. But we would like to have a value of alpha that we agreed upon, that has all the nice property where we can say this is the angular momentum. Just that.
But one thing you haven't said is that there's infinitely many Poincare subgroups of even before we get
because of the super rotation.
There are infinitely many Poincare subgroups of BMS. So somehow, but if you pick out a vacuum, there's a unique one.
Yeah, right.
That is spontaneously broken in the vacuum.
That's right.
And in the case of angular momentum, the vacuum after is different than the vacuum before. So there would be two canonical choices of angular momentum, the one before the gravity wave passed and the one after.
No, there is only one choice. The thing is that you fix it at spatial infinity, and you only have one choice of vacuum, the one that's spatial infinity, and then everything is fixed by Einstein's equation. So
Yeah, but you could also have fixed it at null infinity after the wave pass. That's an arbitrary.
so you have two different definitions of angular momentum because you need to choose your supertranslation frame. So you can choose your supertranslation frame in the future or in the past. It will give you an answer. So it depends on that choice. Yes. But once you fix.
May I ask also a question? So I mean, in these scattering calculations that we all do and love, we pretend that the initial state has a definite angular momentum, right? Energy and angular momentum. And we describe the outcome of the process in terms of those. So are you saying that if you want the initial angular momentum at Sky plus minus or Sky minus plus to be, fixed by the initial kinematics of the problem, that does fix the super translation ambiguity or does not?
Yeah, that fixes uniquely for the entire Sky plus.
And does it fix it?
Whoa. All those.
Does it fix it to make the initial shear vanish?
So yeah, so you choose the initial shear to vanish. So the boundary condition is that you fix the standard boundary condition that everybody is using is that C minus equals 0 at Sky plus.
That's what I thought. But
I don't think so, Gabriel. You're thinking of Feynman diagram calculations, right?
Yeah, for instance.
Yeah, those all are 0. Every Feynman diagram, every exclusive process is 0, and every process you calculate will violate every one of these conservation laws that Geoffrey is writing down.
No, but
that's related to the problem of infrared
to an exclusive process. I'm preparing the initial state. Are you saying that the initial state, the two-particle initial state, gives a 0 result for the scattering process?
Well, with a scattering process, I'm talking about an in state and an out state, not something where we average. If we start averaging, if we're tracing out over photons or gravitons, those carry angular momentum, and angular momentum won't be conserved.
Yeah, but the initial angular momentum is given.
Initial angular momentum is given, and but if you compute an exclusive process, you'll get 0.
Yeah,
so
that's fine, but I don't see any problem with that. I'm not considering exclusive processes. I'm considering any final state. I mean, I have an S matrix.
Oh, you're considering okay.
But the initial angular momentum is fixed. Sorry.
Well, you picked a frame.
Well,
you picked a super translation frame.
Yes, but I'm saying you have to pick that one if you want the initial.
No, there are infinitely many super translations.
Times the impact parameter of the collision.
By the way, we can consider classical scattering, and then, as recent work has shown, the problem of angular momentum loss plays a direct role in the scattering angle. So
yes,
the question is...
the question is of substance, I think.
Yes, and I'm not sure everybody understands the question of the other ones here.
Yeah.
Yeah, I'm not sure I understand what is the...
I thought that there is an ADM angular momentum, and you want to recover that one.
No, there are foliations of flat space for which the ADM angular momentum is non-zero.
So yeah, so let me dispute that also. Yeah, so we don't agree on here, but let me, yeah.
No, there's a paper by Yao from about 5 years ago.
No, but Yao, yeah, exactly. Yao uses alpha equals 1, but if you use alpha equals 0, where the BMS group
but he said ADM. The ADM formula for angular momentum is non-zero. There are foliations of flat space with the property that if you look at the angular momentum at infinity, it's non-zero.
Yeah, it uses alpha equals 1, but
ADM. What I've just said, disputing what Gabriela said, that that the ADM angular momentum is defined in flat space.
I don't believe the statement is correct.
What is not correct?
The angular momentum of Minkowski at spatial infinity is non-zero.
No,
It's a paper by Yao. You want the reference?
I already checked it, but I don't think I agree.
I'm talking about the ADM angular momentum for the two-particle scattering process. At time equal minus infinity.
You're making a highly coordinate dependent statement, and it's something which BMS showed has no canonical meaning in general relativity.
Well,
so to me, if we fix the super translation frame at pi plus minus, you define very well. I mean, you define the angular momentum in that frame.
yeah. I saw in the literature people talking about a special or canonical boundary frame in which the initial shear is 0, and that has a privileged role in fixing the ambiguity.
Yeah, because then you define, this is how you find the intrinsic angular momentum of Kerr, for example. If you want to define, the J of Kerr, it's defined in the Weil tensor. There is a unique way to define it. But if you want to define it from the formula I just wrote down, you need to fix C minus equals 0 to
that's what I thought.
There's also an important distinction when you do Feynman diagrams. You're really doing a quantum calculation. And there's an important distinction between classical and quantum. So in the classical theory, if you have a classical solution, you can go to Bondi frame in which the C vanishes at scri minus minus.
Mm-hmm.
But in the quantum theory, you can have
plus minus, you mean?
Plus minus.
Or scri minus minus or scri minus plus?
No.
Let's be clear.
Scri minus minus. You wouldn't, well, you could do either one, but more natural would be scri minus minus.
Okay, well.
Yeah. So then the evolution equation.
Before you throw any particles, there's G mu nu is eta mu nu. You could do that.
Okay.
But in the quantum theory, you can have states which are superpositions with different C's. And that's important.
Yeah. No,
and you can't set C to 0 in the quantum theory. And in general, if you start with C equals, in the quantum theory, and it's implicit in the Feynman diagram, the outgoing state will be a superposition of different vacua with different C's, which have each one which would have a different associated angular momentum with it.
So if we fix C equals 0 at scri minus minus, it will give you by evolution a C minus, which is non-trivial at scri plus minus. So it will give you a specific boundary condition at scri plus minus, which is also to fix some superposition of C minus.
Yeah.
There. So, but this is encoded in the formula here. I'm just asking to fix C minus at scri plus minus. So that defines.
So if you fix it at scri plus minus and typically match it to scri minus plus, it might be non-zero at scri minus minus, depending on what your data is. So you might be saying that the vacuum had angular momentum before you threw anything in.
I see. I don't know.
And I want to define the moment independently of this. The angular momentum should be encoded in the Weil tensor. It should not be depending on the diffeomorphisms. The intrinsic angular momentum.
Maybe you should go ahead and leave this for tomorrow's discussion.
Yes, yeah. I will add a couple more items. So okay. Okay, so let me go to yeah. So alpha equals 1. So it's another definition. There was a very nice property that was proven by Ashtekar and Magnon in 1982. Which is that there is a way to write down this definition for any foliation of scri plus and not just Bondi cuts. and here is the formula for the angular momentum in that language. So here the language is a bit different. It's using this geometrical formalism, and all these notions are intrinsic to Scribe plus. So it's the intrinsic degenerate metric. Then you have any vector, which is so that L times N is -1. And then you have the intrinsic derivative on Scribe plus. And then this formula is invariant. So the inverse of the degenerate metric is not unique. There is an ambiguity, but the angular momentum is independent of this ambiguity. And so this formula does not rely on boundary coordinates, so on boundary cuts, but it matches the formula I showed you for alpha equals 1. So this such interesting definition is not known when alpha is not 1. So it's not clear it can be done, but to me it's not clear it cannot be done. So I didn't see a uniqueness of this formula. At least I'm not convinced of it. Maybe someone can point me to a literature if there is a proof of uniqueness of such formula, but otherwise, maybe there is a generalization for different values of alpha.
But if the ambiguity is about cutting Scribe plus, I mean, this is the super translation ambiguity, changing the cut.
Yeah, it's more general than that here, because if you change the cut, you are still in the boundary frame. So boundary frame is that is the existence of boundary coordinates. So for any super translation, you keep these gauge conditions, right? You keep these 3 gauge conditions here. But now I can look at different radial foliation where GRA or GR is non-zero, close to null infinity. So that would be a more general foliation than bounding. So it's more general than super translation ambiguity. It's, so you have a lot of more diffeomorphisms you can think of to move.
Yeah, but by the way, the definition you were showing of Ashteka uses conformal compactification. So if peeling is wrong, which is true most of the time, I think, you cannot write it, no?
Very good. Indeed. So that's restricted to the conformal completion formalism indeed. So if peeling is wrong, it depends at what place the logs appear. But if you can define it, yeah, if its peeling is wrong at subleading orders close to Scribe, close to null infinity, then probably you can still define something like this. It's a good.
Yeah.
Good
I'm surprised that you cannot have boundary-like coordinates and nobody cares about the third. Anyway, go on.
Okay, I mean, this was actually, yeah, it was the objection of Abe Ashtekar about this alpha non-1, because alpha equals 1 was like a nice formula, this one, but I'm happy with boundary coordinates.
Sorry, what is phi here in this equation?
Phi. So well, you need to define if you have a vector psi, you have to look at its projection into the sphere, and you have a unit metric on the sphere, and so you can just define a killing vector of that sphere and call it d phi. Specific killing vector of the boundary sphere. So there's always, I mean, an ambiguity, rotation ambiguity of that vector, but that you fix it as special infinity. Okay, so here are the expressions for the flux in post-Newtonian expansion of this angular momentum. So here's the expression of Thorne that's written in Thorne, and the expression of G is given here. So we derive with Roberto and Ali, just talked here. So the first one is a classic expression. So this one is non-classic. Actually, it was derived by Epstein and Wagoner in 1973 at 3.5 Pn order, and we derived the whole Pn expansion of it using the definition. I'm not sure it was written down before. There was a distinct expansion found by Blanchet and Fayet. So the distance.
Fayet, phi, by the way, phi.
Phi?
Yes, not Fayet, phi.
Ah, Fayet, sorry. Sorry, Fayet.
No, phi.
Phi. Ah, yeah, okay, phi. Okay, sorry, phi. So then the flux is given here. There's a dot missing. So
at the end, are you saying one expression is wrong, one is correct? What is the proof that something is correct for the center of mass?
So so in terms, I would say one expression represents the center of mass, the other one is the center of mass up to a term which represents something else. So so I would say one is more correct than the other. Yeah, in the sense that one is the center of mass, one is not. Yeah, I would say it this way. So this expression was found using pseudo-tensor. Well, I'm not sure. Yeah, some pseudo-tensorial methods using the Landau-Lifshitz pseudo-tensor. And then the difference of the two between our expression and the one of Blanchet and Fay is an exact boundary term. So overall, if you have flux balance laws, you can always remove a boundary term from each side of the flux balance law. So in that sense, the flux balance laws agree. We agree on the flux balance law, but we don't agree with what is the surface charge. And actually, the one they found does not match any of the formula that I wrote down with any value of alpha, which is here. So it cannot be written in a covariant way over the sphere using this formulation. So this is why I would object that this is a nice definition, because you cannot write it in a covariant way using this language of boundary frames in a covariant way. But if you put alpha equals 1, then you find this one. So I would say this is the generalization of the Thorne expression. For the center of mass. So now you can ask if canonical Lagrangian or Hamiltonian methods give you a preferred one, a preferred charge, and that's not really clear. I see I'm getting over time. Okay, so I should probably just get to the final point here. So the point is that the generalized BMS charges can be represented as spatial infinity. So if we have alpha equals 0, the standard BMS algebra that I showed earlier can be generalized to this algebra, which is now R is a diff S2. And this bracket is the standard bracket at spatial infinity. And that works only for alpha equals 0. So if you have alpha non-zero, you get an anomaly in these brackets. And this anomaly is not something you want at spatial infinity, because there's no reason you will have an anomaly of these brackets at spatial infinity. There's no flux at spatial infinity. So we would expect that we have standard commutators. And so in terms of representation of the generalized BMS, that favors alpha equals 0. This is the main argument for why alpha equals 0 is interesting. So maybe, well, so the thing is that if we like these diff S2 charges, we want them to have a nice algebra, and that algebra is nice only for alpha equals 0. All right, so I already put that point here. So now if we have this algebra where alpha equals 0, actually all the BMS vacua have identically 0 BMS charges. So also if your Weil tensor vanishes, then all charges are identically 0. For alpha non-zero, the charges are the standard BMS charges are 0, but the generalized BMS charges are non-zero, given by this formula. So if you have a diff S2, So you see, if you have a SO31, this is 0 actually. You can check it's 0. But if you have a diff S2, it's non-zero. Or if you have a Virasros, it's non-zero. But it depends on alpha. So alpha is 0, just everything cancels. And in the literature, yes, alpha equals 1 was used in 2016. And so I also, I claimed there were super rotation charges associated to the fact that you act with generalized BMS transformations. But I would step it back now and say, actually, no. At special infinity, the representation occurs of BMS is true only for alpha equals 0. And for that case, actually, all the charges are identically 0. So there's no BMS charges for soft hair, for if you act with BMS diffeomorphisms. They are all vanish. And then, so that was the point about alpha equals 0. And then, well, the last point is to identify the center of mass frame, and that's more standard. I will just mention that. So to isolate SO3 inside of SO3, 1, one needs to keep track of the angle of the momentum that is radiated because of this Bondi mass loss. So the way out is to identify the right vector and to find the vector, to isolate the vector inside of SO31. And so that was found in a nice paper by Shtekar, De Lorenzo, and Kera. And I independently checked it with David Nichols using a different argument. And that depends explicitly on the value of P. So then it's, so this definition is non-local, the definition of the vector, because the momentum is defined in a non-local way. This is defined as an integral over the sphere. And so this vector becomes a non-local definition. So to be able to isolate the center of mass frame, we need some non-locality. Okay, so since I'm over time, I don't think I have much more time to discuss the non-locality, but that's more like related to what Yao was doing recently. But I will just skip that. And just to mention that in the formula I wrote down for alpha can be written maybe for some of you in a nicer way, this way. So here is the formula written by whom? By many people, Witt, and then Maggiori's book. This is the way the angular momentum is written down as well. It's from the Landau-Lifshitz pseudo-tensor. You get this formula. So you can check it's equivalent to what I wrote, and then the alpha ambiguity is here. So you get an extra term, which is a total derivative term. And so in the post-Minkowskian formalism, since we have this property that the trace-free part of H is independent at first order, alpha ambiguity appears at order G squared. So, so in this nice analysis, the recent analysis of Thibault, alpha 1 was used and consistently everywhere, and that's that. One compares with different papers, one has to check that the definition is the same. Okay, just to mention that. I will stop here.
Okay, let's thank Geoffrey. So, and we have time for questions. So are there any questions?
May I ask a question? You were writing formulas for the center of the boost constant, Ki. Yes. So do you have the Poincaré algebra satisfied now by, you have the full J mu nu and P mu?
Yes.
You have selected a Poincaré subgroup. So is the Poincaré algebra satisfied?
Yes, yes, the Poincaré algebra is satisfied, yes. So it's a sub, because for any value of alpha, you have the...
For any value of alpha.
Yeah, you have this algebra, and the sub-algebra of this is Poincaré. Then, yes. So
and these quantities would correspond to, now I'm lost, to ADM, not initial fine. I mean, what would be these total angular momentum, including the center of mass? This is ADM-like, or at I0, how is it called?
So at special infinity, Yeah, at special infinity, if you go in the standard center of mass frame of Kerr, it reproduces just.
Oh, but Kerr, please. I mean,
yes.
we're not discussing Kerr otherwise.
Yeah, but okay. So if you, so maybe I'm not understanding the question.
I mean, you have selected from ambiguity, from BMS ambiguity, you have selected a Poincaré subgroup. So I want to understand physically what we are talking about here.
So yeah, so here you have to fix a BMS frame, so a super translation frame, right, at special infinity. So the one, so to define the angular momentum, yeah, right. You want to fix.
So you use C plus equals C minus equals 0.
C plus, no. C plus is not, cannot be 0 at the same time as C minus. That would violate Einstein's equations. But
these are antipodal identified. So
no. Well, it depends what you mean by C plus. Here, C plus is the one that's correct plus plus. So it's the difference with C minus is related to the displacement number.
I meant.
So here is the C minus. So I didn't have time actually to show you maybe this formula. Right. So if you want to write the angular momentum in an for arbitrary C, you need to write down this, the invariant formulation. So here, so far, I wrote it for C minus equals 0. But if you wanted to write in an arbitrary super translation frame, you need to write this formula then. So this is the intrinsic angular momentum in arbitrary super translation frame. So for arbitrary choice of C minus, it will give you the angular momentum. So you subtract the effect of the frame, of the super translation frame.
But what is this C?
This little c is the velocity of light.
Yeah, no, the big C.
And the big C is in the decomposition of the shear is UL, is the electric part of the radiative multiple moments.
At any U.
At
it's a function of U now.
Yes, it's a function of U. You could write it at any U, yes, but here, yeah, right, at any U.
So psi will be non-zero at generic U, right? Is that right?
Yes, that's right. So this VL or psi is non-zero at generic U.
Is it right to characterize this by saying that you choose a super translation frame associated with spatial infinity, and then this is the angular momentum that preserves the vacuum.
That's right. So exactly. So this is the formula which exactly says that. So you pick up, you say you normalize, you pick up your angular momentum with respect to the frame at spatial infinity. So you say you want to remove the effect of the frame at spatial infinity to write down your angular momentum, and then you want to write down a formula such that you can read your angular momentum at any U, and where it will be super translation independent, because now you can check that this formula commutes with P. So you can check that algebraically, it will just commute with P. So you will not, you choose really you fix all the super translation and the translation frame by choosing this C. So it's a bit more than the radiative multiple. You complete it with the L equals 0 and L equals 1 harmonica as well to write down this C. You pick up also your position, four position, and then you totally define the J that commutes with all the P, including the translations. So that would be the intrinsic angular momentum. So is so I would say that's the way to define this, and then the algebra is the same algebra as before, because well, you can check that it's obeyed algebraically. And then once you actually, even better, once you pick up, well, it was really the end of the talk, but if you pick up the R, or if you pick up the R, which is the right vector at any U, which selects the SO3 group, since this R depends on P, And since I just told you that it commutes with P, you can actually replace this R by R intrinsic, and that will still obey this algebra. Yeah, so then this one will be the intrinsic definition. So here everything was defined as scribe plus minus, and so all this algebra is really checked at scribe plus minus. I don't claim it is true at any scribe plus. That maybe there was a way to do this, but we didn't do that. But so far, this definition makes sense really at special infinity, and this proposal for how to extend it at scribe for these invariant supertranslation dependent definitions. But I just get all the nice brackets at special infinity.
So if we have some solution that corresponds to incoming gravitational waves which scatter and then go out, and if we use this definition of angular momentum, typically we'll get something non-zero. It's scribe minus minus and scribe plus plus for the vacuum.
So this definition for the vacuum, it's always zero.
Well, okay, but in the far future, because you've shifted your super translation frame, the super translation frame at scribe minus minus won't be the same as it's at scribe minus plus.
Right.
So if you make it zero at scribe plus minus, it won't necessarily be zero at scribe plus plus. So we won't necessarily see angular momentum conservation, right?
I don't understand. I thought at scribe plus minus, it is not zero, this J. Are you talking about this J?
Right.
It is zero at J.
It could be zero. Let's imagine a case where it is zero there.
Plus minus.
We could, yeah, just for simplicity, we could imagine a situation in which you have a conspiracy with your incoming data so that it's zero at scribe plus minus, but then it might be non-zero at scribe plus plus or scribe minus minus. Is that right?
I have to think about this. Yeah, I understand your question. I'm unsure about one thing. Let me answer this tomorrow.
So
would the answer depend on the value of alpha?
No, because anyway, the alpha will be a transient effect, because all the alpha dependence disappears at past and in the future, because it's.
No, but here we are transient because we are comparing minus infinity to the special infinity, which is halfway, no? Okay.
Well, we look at the difference between scribe. The question of Andy, I guess, is between scribe plus plus minus the value at scribe plus minus, right? So that's so it can be evaluated just at the boundaries. So the transient effect should not matter for this argument.
Is the boost charge of the vacuum zero for this definition?
The boost charge, yeah, is also valid. Huh? So this is the same definition. It's the same definition. Is also the boost here.
DARA is zero for angular momentum, but not for the boost.
Right, for the boost. Yeah. So these terms are here too. Huh? This is the same definition. It's for the entire Lorentz here. Maybe we should rediscuss that. Yeah, but we still have some minutes. Okay. So tell me the C. So let me just take the NA. You see, if we have an explicit value of NA, it's easier. Let me just think loud. So here's the explicit value of NA for n particle scattering.
okay.
But now you tell me I can write down the same formula at scribe plus, where now the C minus will be replaced by C plus, which will be different than the previous one.
Yeah.
That's right. So indeed, there will be an MDC plus there. And then if I substitute that into the formula, that is where you're getting at here, right? So here, what oh, what's happening? So here I will replace with the formula, which will be 2m CDA of the C plus. So here in this formula is with the C. Well, is the this formula actually is the C that evolves. That's the point. Yeah, the C evolves here. So that formula reduces with the C plus. Yeah, so it depends. Yeah, right. It depends if we use the C that evolves or if we use the C at special infinity. To answer your question.
Well, using the C that evolves is equivalent to saying you'll change your angular definition of angular momentum in the
you keep adjusting it. Right.
future so that it is zero.
Yeah, that's right.
But if you have a fixed definition,
with respect to the frame at in the past. So if you put the C minus here, yeah, right. If you put the C minus here, all what I said here in terms of the brackets remain the same because anyway they are a special infinity. So so they differ in the proposal of what we mean by the angular momentum. But indeed, if you put the C minus here, then you will get the extra term, which will be indeed m, something like m dA of C plus minus delta C, which is non-trivial because of the memory. And so there will be the bonding mass aspect is non-trivial. So there will be a term, there will be a difference, yeah.
Sorry, there is also a linear U term in that expression for an A. If you go back. Yes.
Yeah, but that one is for boost only, because it's a total divergence, right? There's a dA here. So that does not matter for the rotations. Each time you talk about boost, there is always a term linear U because the center of mass just moves linearly. Well, there's a momentum a priori, and you have always a U linear term that generally appears, but not for the rotations, right? Because of this dA here.
Yes.
So I agree with you, Andy. Yes. So if you take the C minus here to define the angular momentum normalized with the super translation frame at special infinity, and then evaluate this one at square plus plus, then I can replace NA with the expression where I replace everything at C plus. There will be these terms appearing, which a priori is non-zero. Which is a change of angular momentum due to the displacement memory effects. Yes. So this is what was your point before, that the angular momentum is non-zero.
Yeah.
For Minkowski, but this is because this is because of the way you normalize the angular momentum with respect to a specific boundary, or But that was the point.
There's an infinite degeneracy of vacua, and they have different angular momenta. And there's one for every BMS frame. There's one for every vacuum. There's one Poincare group that is not spontaneously broken, and that singles out a preferred angular momentum. But anytime we do any scattering experiment, we have a transition from one vacuum to another. That's the memory effect. So, yeah. So but I mean, I don't think we knew what exactly the expression was for the one that, that's what I think you've explained here. I don't think we knew what the expression was for the one that preserves the vacuum, but there is some ambiguity about whether you would want to sort of use as your canonical frame the one in spatial infinity, or one in the infinite past, or the one in the infinite future. But they would give different answers.
Yeah, I agree. They would give different answers.
Yeah.
Okay, well, I think it's pretty clear now. Any other questions from me?
Okay, so why don't we thank Geoffrey again and then set up for Miguel's talk. So thank you.